I think at the beginning what I'd like to do, just so that you have some kind of orientation, my lecturing style and also the topics that I'm going to be talking about they're a little bit different than what Will was doing this morning. Dynamical systems. I was originally going to start off talking about dynamical systems, but then I switched things. So the next thing that I'm going to talk about, I'm going to talk about lattices in locally compact groups. This is probably going to be next week when I take up my lectures again. And the next thing that I'm going to talk about is I'm going to talk about ergodic theory and entropy theory. This is probably going to be review for some of you, especially for those of you who have a little bit of a stronger background in dynamics. But for the sake of people who don't, I want to go ahead and at least review the main results that I'm going to need from entropy theory. The next thing that I'm going to talk about, so this is all kind of review material. And the next thing that I'm going to talk about is I'm going to talk about a theorem called Furstenberg's orbit closure theorem. Next, I'm going to talk about a conjecture called the Furstenberg conjecture. And I'm going to talk about some results towards the Furstenberg conjecture, which are Rudolph's theorem and some of its variants. Rudolph's theorem and variants. And finally, can you guys read at the bottom here? Can you guys in the back see at the bottom? Yes? So the last thing that I want to talk about is I want to talk about an application of these ideas to the mixed Littlewood conjecture. To the mixed Littlewood conjecture. I'm going to abbreviate Littlewood conjecture as LC. I'll write it on the board in a moment. Okay, now I guess what I should say is that when I was preparing these lectures at the beginning, I felt kind of ambitious, and I wanted to try to get to some of the really big theorems and applications of dynamics to Diophantine approximation. There actually are a lot of really big and impressive theorems out there now. Have some of you guys maybe heard about like Einsiedler, Katok, and Lindenstrauss's proof that the set of exceptions to the Littlewood conjecture has dimension 0? So that's one of the reasons why Lindenstrauss won the Fields Medal. It's a major result in this field. What I realized when I was preparing these lectures is that there's actually a lot of background material that I felt like I couldn't assume that everybody knew. And since it's a summer school, what I'm going to do in the end is going to fall a little bit short of trying to explain the proofs of those major theorems. Instead, my emphasis is really to try to give you some of the tools in the background that you need in order to get into this subject and understand what's going on. I hope that's okay with everybody. But if you feel like I'm going too slow, at any point you can let me know. And I will speed up as fast as you want. Let's begin by doing, so just to get an idea also what you guys know and don't know, does anybody in here know about Furstenberg's orbit closure theorem? Can you raise your hand if you know? It's a times 2 times 3 problem. A few people do know, but maybe most people don't. So then I don't really expect most of you to know about the Furstenberg conjecture and the rest of the stuff that I'm talking about. Okay, so I think that's probably a good thing. So in the beginning here, I want to talk about Diophantine approximation. I want to give you a little bit of a review of what this subject is about and some of the main results. Diophantine approximation is the study of how well real numbers can be approximated by fractions. At least that's what it is classically. In modern times, it's also sort of grown to encompass approximating numbers in other settings by subsets of whatever setting you're working in. But the part that I want to focus on is kind of the classical part. And one of the first theorems that you probably would learn about if you're learning about Diophantine approximation is Dirichlet's theorem. So this is Dirichlet's theorem in Diophantine approximation. It's proved, I guess, in the 1830s. And what it says is that if you have any real number alpha, and if you have any number, natural number n, you can always find a fraction a over n with, let's just say an not equal to 0, 0. This is for technical reasons later. With absolute value of n less than or equal to n, and such that the distance from alpha to a over little n is bounded above by 1 over little n times big N plus 1. Hey, can you just so I can, again, get to know my audience a little bit, can you guys raise your hand if you've seen this theorem before or seen it proved before? It's a very basic result. If you take an elementary course in number theory, you've probably seen it before. It's a good application of what's called the box principle, Dirichlet's box principle. And, well, by the way, it's also best possible in the form that I've given it here, in the sense that if you fix a value of capital N, you can always find a real number alpha for which the right-hand side can't be decreased at all. Okay? If you don't really care about that level of precision, you might have seen Dirichlet's theorem stated in slightly different forms. So a corollary of what I've written here is that if you have an irrational number alpha, then there are infinitely many fractions a over n with distance from alpha to a over n less than or equal to 1 over n squared. Okay? I want to write the theorem this way also because I want to use this form of it to compare with some other statements that I'm going to make later on. For those of you who have seen this before, does any of you know how to prove it besides using the Dirichlet box principle? Do you have any other ideas how you might try to prove that? There's many different proofs of Dirichlet's theorem. There's probably at least 7 or 8 different proofs that I've seen, genuinely different proofs. One way that you might see is by using what's called the theory of simple continued fractions. And I want to just make a quick digression and talk about continued fractions. My purpose, and all of the things that I'm talking about are selected topics from Diophantine approximation. And my purpose in choosing these specific topics is because in just a moment I want to try to explain how you can reformulate all of these theorems and results in terms of dynamics in different spaces. Okay, so now I want to talk about continued fractions. And some of you might have seen simple, I'm sure that you've seen some simple continued fractions before at some point in your mathematical or scientific career. So I'm just going to state some facts here without proof. If I have an irrational number alpha, for any irrational number alpha, there is a unique sequence of integers a n, n going from 0 to infinity, with a naught in z, all of the rest of the an's bigger than or equal to 1, and for which alpha is equal to a naught plus 1 over a1 plus 1 over a2 plus 1 over dot dot dot. Okay? What I mean by the expression on the right-hand side, of course, is that you go out to n and then you take the limit as n tends to infinity. So I'm saying that that limit exists and it converges to alpha. Okay? Shorthand notation for this, because you don't want equations stretching down the board in that kind of a way. Well, one shorthand notation that I use is to write brackets and then put the first number here and then a semicolon in the rest of the numbers. So these numbers are referred to as the partial quotients in the continued fraction expansion of a real number alpha. And there's another collection of important quantities which are associated to the continued fraction. They're what you get by stopping this infinite process at some finite step. So for each natural number n, actually let's just say for each n bigger than or equal to 0, let's define the rational number, Pn over Qn, to be what you get by running the continued fraction expansion out to n and then stopping. Okay, that's going to be a rational number. I'm going to assume that I've chosen Pn and Qn so that their GCD is 1. And I'm also going to assume that Qn is positive. Okay? These numbers, by the way, they're called the principal convergence in the continued fraction expansion for alpha. It's pretty easy to check. You can just try to prove this directly if you like, if you want to do something fun. But I bet all of you could prove it. So it's pretty easy to check that the numerators and denominators of the principal convergence rather satisfy the recursion equations. Pn is an times pn minus 1 plus pn minus 2. And qn is an times qn minus 1 plus qn minus 2. So this is going to be true for all n bigger than or equal to 2. And the reason why these fractions are important is because these fractions, the principal convergence, actually give they tell you how well the number alpha can be approximated by rationals. They give you the best possible rational approximations in a strong sense. Okay? So to be precise about what I mean, I'll just draw you a little picture here. I'm not explaining everything to you, obviously. You have your number alpha sitting here somewhere on the number line. On one side of alpha, you have the n minus first principal convergent, pn minus 1 over qn minus 1. On the other side, you have the next principal convergent, pn over qn. And then back on the other side over here again, you have another number, which I'm going to call pn minus 1 plus pn over qn minus 1 plus qn. Okay? So you have to believe me that this picture is actually correct. But if you believe me that this picture is correct, well, you have to believe me about one other thing, which is you have to believe me that the numerators of the difference of any pair of fractions here is 1. If you believe that, then what you can see from this picture is you can see that the distance from alpha to pn over qn. So let me see if I want to do pn over qn or pn minus 1 over qn minus 1. I'll do pn minus 1 over qn minus 1. Yeah. Okay? On one hand, it's less than or equal to the distance between the outer two endpoints here, which is 1 over qn minus 1 times qn. And on the other hand, it's bigger than or equal to the distance between these two fractions, which is 1 over qn minus 1 times qn plus qn minus 1. Okay? Now, if I put my recursion relations into this pair of inequalities here, what I find is on the left-hand side, well, okay, something that would be definitely smaller than qn plus qn minus 1 would be an plus 2 times qn minus 1. And so on the left-hand side, I have 1 over an plus 2 times qn minus 1 squared, less than or equal to distance from alpha to pn minus 1 over qn minus 1, less than or equal to. On the right-hand side, I can replace the fraction that I see by 1 over qn minus 1 squared. Okay? That's something which is going to be bigger than the right-hand side on the previous line. And so I have this pair of inequalities, which is essentially best possible. Okay? And when I say that, what I mean is that this pair of inequalities tells you how well. Oh, I forgot an an. I forgot an an here. Let me put it in there. An times qn minus 1 squared. Okay. This pair of inequalities tells you the real truth about how well alpha can be approximated by these numbers. Okay. Now, what I haven't really explained, I just told you in words, is that the rational numbers pn minus 1 over qn minus 1 or pn over qn. They're the best rational approximations to alpha. What that means is that if you use all the fractions with denominator up to that denominator, you're not going to find a better rational approximation. In fact, even if the denominator goes up to the next denominator of a principal convergent, you're still not going to find a better rational approximation. Okay, why am I telling you all this? I'm telling you all this because understanding these numbers, these ans, these partial quotients, it will tell you how well approximable a number alpha is by rationals. Okay? I'll also point out one other thing about the simple continued fraction expansion, which is that Dirichlet's theorem just tells you that there exists a rational number which does what you want. But the continued fraction expansion actually tells you how to calculate that rational number. And so it's good from a computational point of view as well. OK, now let me come back over to here. And let me tell you about my next thing, which is badly approximable numbers. badly approximable numbers. Okay? So if you look at this inequality that I just now wrote on the board, on the right-hand side, if I get to some denominator qn minus 1, and then it turns out that the next partial quotient that I see is actually really, really large, it means that I'm going to have a really, really good approximation to alpha, right? So Dirichlet's theorem tells me that I can always find a rational number a over n with distance from alpha to a over n bounded above by 1 over n squared. But it could actually be the case that I get a much better inequality than this. In fact, it turns out that if alpha is irrational, you can put a 1 over square root of 5 n squared on the right-hand side here, and the statement is still true. Okay? But you can't do any better than that. And so people who studied this a long time ago, they realized that there are some numbers, alpha, with the property that the best that you can hope for in terms of a theorem like this is improving the constant in Dirichlet's theorem, and that's it. So let me make a definition here. For every epsilon bigger than 0, I want to define a set which I'm going to call bad epsilon. Bad epsilon is going to be the collection of alphas. I'm just going to restrict myself to the unit interval here. The collection of alphas in the unit interval with the property that the infimum of n times the distance to the nearest integer of n alpha is bigger than or equal to epsilon. Okay? By the way, for people who need to look at this more carefully, if I multiply both sides of this inequality by n squared, and then I let a run over all possible integers, all possible, yeah, question?
Sorry, I think I missed this. What's the norm of n alpha?
I'm about to explain that.
Oh, okay.
Yeah, I'll go ahead and write it right here. So what this is this is the min over all a and z of the distance from x to a. Okay? Distance to the nearest integer. Distance on the circle.
Right.
So this corollary says that for every alpha, you can find infinitely many fractions with distance from alpha to a over n bounded above by 1 over n squared. If you multiply both sides of this inequality by n squared, you can restate this by saying for any alpha in R, well, I guess here what you have to say is the lim inf as n tends to infinity of n times double bar n alpha is less than or equal to 1. Okay? So that means that there are infinitely many. Once you pick a denominator n, it should be clear which numerator you should use. You pick the one that's closest to your number that you're trying to approximate, right? And so once you've fixed n, this distance is minimized by taking the minimum over a and z of the distance from n alpha to an integer. Okay? So badly approximable numbers, these are precisely numbers for which you can only improve the constant on the right-hand side in this corollary, and that's it. Okay? And how do you, just to see if people are understanding, let me also write here another definition. If I just talk about bad, I mean the union over all epsilon bigger than 0 of bad epsilon. So just to make sure that people are understanding, how can I characterize badly approximable numbers? This question is actually for people who didn't already know the answer before the lecture. How can I characterize badly approximable numbers in terms of the continued fraction expansion of a real number? Who knows the answer? Can you raise your hand? I know that you know it. Just kidding.
Well, can't you use your ANs to determine that? Because aren't they controlling how you can approximate things?
So how would you reformulate what it means to be badly approximable as a statement about the ANs? You're right, by the way.
You would have to know that essentially like the ANs, since they're acting inversely, would have to be very, very small.
Well, they'd have to be bounded, right? So if you take a look at the inequalities on the right-hand side of the board over there, and if you believe what I told you about the principal convergence being the best rational approximations to your number alpha, here's an alternate characterization of what it means for an irrational number to be badly approximable. An irrational number is badly approximable if and only if there exists a c bigger than 0 such that all of the partial quotients of that alpha, I'm including the dependence on alpha here, are bounded by c. Okay? Make sense? So that's an alternate characterization of what it means to be badly approximable. Okay, now, so now, next question. What can you say about how big the set of badly approximable numbers is? Are there badly approximable numbers? Well, that's pretty easy to see, right? You could just take the number whose continued fraction expansion is all ones, better known as the golden ratio. That's your first example of a badly approximable number. In fact, you can just put a bound on, you can say I want to take the collection of all real numbers with partial quotients bounded by 3. Those will all be badly approximable numbers. So what can you say about the size of the set of badly approximable numbers? It's what? It's uncountable, actually. Think about using ones and twos. You can find uncountably many different real numbers because for every different choice of the ANs, you get a unique real number. Okay? So the set of badly approximable numbers is an uncountable set. It's actually even a little bit bigger. There's a little bit more that you can say about it. But on the other hand, it's not too difficult to prove. And in fact, I think I can convince you that this is true in not too long once we talk about the dynamic stuff. That's not how these guys proved it. It's not too difficult to prove. In fact, it's actually, I got to admit, it's actually easy to prove that the collection of all badly approximable numbers has Lebesgue measure 0. Okay? So this is proved by Borel and then by Bernstein. I'm pretty sure they had independent proofs, 1909 and 1912, something like that. The Lebesgue measure, lambda here is Lebesgue measure of the set of badly approximable numbers is 0. Okay? So it's a set of measure 0. Now, I'm sure that you're probably, I'm just thinking ahead to what Anish might possibly say. And maybe I can tell you one other thing. I wasn't going to say this, I wasn't going to mention this, but for the sake of people who know about Hausdorff dimension, there's also a theorem by Jarnik. It's in the 1920s sometime, I think about 1926. And what Jarnik proved is that the Hausdorff dimension of the set of badly approximable numbers is actually 2. Okay? So the first result here says that if what you care about is Lebesgue measure, then the set of badly approximable numbers is negligible. It's a set of Lebesgue measure 0. On the other hand, if what you care about is the Hausdorff dimension of your set, then it's actually a very thick set. It's sort of the next best thing to having a set of positive measure. Say it again? Oh, I mean the dimension is 1. Think you can't have a set. Thank you. Was that confusing?
Very.
That would be really, really exceptional. That would mean that we all misunderstood the definition of Hausdorff dimension. No, the Hausdorff dimension is 1. Okay? That means that if the Hausdorff dimension is just positive, that already means that the set is uncountable. Okay? And so to have Hausdorff dimension 1 means that it's extremely thick. It's the next best thing to saying that it has positive measure, although it actually has the measure 0. Okay? So let me tell you a little bit more.
How about its category?
How about its category? I don't know. Oh, yeah, you're the right person to ask about that. Yeah. Okay, let me tell you another theorem, which is, this is just a sort of, well, I was going to say this is sort of to complete the picture. This is not going to complete the picture, but this is another important result along the way. And this is a theorem of Kenshin. It's pretty often quoted. It's from the 1920s, 1924, 1926. And what it says is this. Let's suppose that I have a function psi, which takes in natural numbers and spits out, well, positive or non-negative real numbers. And let's suppose that this is a decreasing function. Okay? This is kind of an important assumption. So let's suppose that psi is decreasing to 0. This is an important assumption in the statement of the theorem. So then there's basically two possibilities in terms of Diophantine approximation for what can happen. Possibility number 1, if the sum n equals 1 to infinity of psi n diverges, then for almost every alpha in R, there are infinitely many solutions, infinitely many a over n in Q with distance from alpha to a over n less than or equal to psi n over n. Okay? Part 2. If the sum converges, then for almost every alpha, only finitely many solutions. Okay? Same sentence, but the conclusion is that there's only finitely many solutions. Okay? So who in here has seen Kenshin's theorem? Can you raise your hand if you've seen this theorem before? A few people have? Yeah? Well, I don't really know how, maybe I haven't really given you guys enough time and context to think about this, but the second part of Kenshin's theorem, does it remind you of any other result in basic probability theory? Yeah, it is an application of the Borel-Cantelli lemma. It follows directly from the argument from the Borel-Cantelli lemma. Okay. I'm not going to really go into that, but you're exactly right. So for each value of n, you can consider the collection of all alphas in the interval from 0 to 1, which satisfy this inequality. That's a subset of the interval from 0 to 1. It's a unit of intervals. It has a certain measure. The measure of the set is psi n, is 2 times psi n, okay? Because the diameter is 2. I guess I'm also assuming that psi is less than or equal to a half, okay? And so if the sum of the measures of those sets converges, then it means that almost every alpha falls in only finitely many of them. That's the Borel-Cantelli lemma. Now, you may know, if you studied a little bit of probability theory, that if you're in a probability space and you have a sequence of events which is independent or even pairwise independent, then if the measures of your sets diverges, then you can conclude that for almost every alpha is an infinitely many. That's under the assumption of independence. Now, the sets that I just described to you, these subsets of 0, 1, they're not independent. But so what Kenshin's theorem is saying is that in this setting, even though you have these sets which are not actually independent, you still have a converse of the Borel-Cantelli lemma. And what does the theorem mean for those of you who are still trying to digest the statement of the theorem? Well, what would be an example of a choice of psi that I could choose for the first one? I could maybe choose 1 over n log n, let's say. Try to choose something which is close to the border. So for example, for almost every alpha, the inequality distance from alpha to a over n less than or equal to 1 over n squared log n has infinitely many solutions. But the inequality distance from alpha to a over n less than or equal to 1 over n squared log n to the 1 plus epsilon has only finitely many. Okay? If you think about what this means, Dirichlet's theorem tells you can find infinitely many a over n's where distance from alpha to a over n is bounded above by 1 over n squared. Now that's true for every alpha. If you only want a result which is true for almost every alpha, Kenshin's theorem tells you that on the right-hand side you can put 1 over n squared log n here. Of course, you have to throw away a set of measures 0. Kenshin's theorem also tells you that if you try to do a little better than that, you'll fail. For almost every alpha, you'll only be able to find finitely many rational approximations that are that good. Okay? So this is Kenshin's theorem. And now, like I said, what I'm telling you is it's a sparse cross-section of Diophantine approximation. I'm choosing results that have nice dynamical interpretations that we can come back to later on. And the next collection of results that I want to tell you about here are results from multiplicative approximation. And this is going to be pretty quick, and then I'm going to start talking about dynamical interpretations. Multiplicative approximation. And let me also check how I'm doing on time here while we're at it. All right, good. So let me just try to get to the point here. So what we've said already, I'm going to tell you one of the main conjectures in this subtopic here, which is the Littlewood Conjecture. This is a conjecture which is more than 90 years old, and it's a famous conjecture in Diophantine approximation. Like I mentioned before, one of the reasons that was quoted in the report why Lindenstrauss got the Fields Medal is for his work on this conjecture, and a lot of other people have made major, very beautiful and significant advances on the conjecture. So let me tell you what the statement of the conjecture is. The conjecture says that no matter what real numbers alpha and beta you choose, the quantity lim inf, you can actually just put inf here if you want, but I'll put lim inf because historically that's what people write, of n times distance to the nearest integer of n alpha, distance to the nearest integer of n beta is equal to 0. Okay? So if you follow what I said about badly approximable numbers a few minutes ago, if I didn't have the second piece here, the double bar n beta, if I only had n times double bar n alpha, well, then I already know that there would be this set of Hausdorff dimension 1 where the conjecture is not true. So what the Littlewood conjecture is doing is it's throwing in this extra piece, distance to the nearest integer of n beta. Remember, that's always something which is less than or equal to a half, but sometimes it's a lot smaller than that. And the hope is that by having this extra piece in the product here, you can make it so that the product of these three terms always can become arbitrarily small. Okay? I'm going to talk a little bit about this conjecture later on. I'm not going to give you a full survey of all the results on this because that's not really the main point here. I guess what I will tell you, though, just as a point of reference and for people who are interested in thinking about this, is there's actually a stronger version of the conjecture floating around now, which people still don't know how to prove. And I think that this is kind of a promising thing to look at if you're looking for a research project. And people call it the strong Littlewood conjecture. What it says is that for all alpha and beta, if you look at the lim inf as n tends to infinity of n times log n times double bar n alpha, double bar n beta, that's finite. Okay? So of course the strong Littlewood conjecture implies the Littlewood conjecture. But nobody even knows whether or not there are any counterexamples to this stronger form of the conjecture. Okay. Now I'm going to tell you about one more conjecture and that is going to fit in nicely to the dynamical stuff that we're going to talk about. Later on I'm going to come back and revise this conjecture a little bit. So right now I'm going to tell you a slightly simplified form of the conjecture. I'm going to call it the p-adic Littlewood conjecture. Later on I'll come back and I'll tell you what the full conjecture is. The full conjecture is called the mixed Littlewood conjecture. It's the p-adic Littlewood conjecture. It's a conjecture which is proposed by Diophantine and Toulier around 2000 sometime, 2000 or 2001, 2002. Diophantine and Toulier. And what it says is that for any real number alpha, and for any, I'll just write prime p. It can be for any integer p bigger than 1, but I'll write for prime p. The lim inf, you can put inf here if you like, as n tends to infinity of n times the p-adic absolute value of n times the distance to the nearest integer of n alpha is equal to 0. Okay? P-adic absolute value, I will talk, when I talk about locally compact groups, I will talk about the p-adic numbers. Right now we're just talking about the p-adic absolute value of an integer, so let me just tell you what it is. It's nothing actually that mysterious. So every integer n, you can write it as p to the k times m, where k is bigger than or equal to 0 and GCD of p and m is 1. And then the p-adic absolute value of that integer is defined to be p to the minus k. Okay? So you take out the highest power of p, which divides your integer, and then you take the reciprocal. Okay? So this is when I first saw this conjecture, I thought that it looked a little phony, actually, or sort of like a contrived thing. But then the more that I thought about it, the more I started to see the reasons why people propose this as a conjecture which is similar to the Littlewood conjecture, but might be slightly easier. In fact, nobody knows how to prove this conjecture either. I mean, we know how to prove that it's true for almost every alpha. In fact, even with an extra log squared n in there. But to prove that it's true for every alpha, that's another open problem. And it's also received a lot of attention. Okay, now that is basically the setting that I want to have in the background so that we can look at these problems and try to see how they're connected to certain problems in dynamical systems. Come back to here now. So I now want to try to get out some dynamical formulations of these problems. I guess one of the themes that is behind all this is that there's not just one right way to think about the problems. There are actually many different dynamical systems that you can use to study the problems. And some are simpler than others for particular reasons. Okay, so the first thing that I want to talk about, and this is in the context of these results like the Borel-Bernstein theorem, badly approximable numbers, etc., is I want to talk about the Gauss map. Okay. Now let me check time, because I need to make sure that I have enough time to get to my number 2 example. In fact, let me do this. Let me leave a space right here. This should be the number 1. This should go in the number 1 slot, so I don't want to interchange the slots. But let me just leave a space right here, and I'll come back and fill that in, because I need to make sure, because Anish told me to make sure and talk about the next thing, so that he can have it for his lecture, and so that Anthony can talk about it in the problem session today. I want to talk about the formulations in the space in terms of spaces of lattices. Okay. And the basic idea here is that in order to study quantities like n times the distance to the nearest integer of n alpha, what we can do, and what people do, is you separate out these two quantities. You separate out the n part and the distance to the nearest integer of n alpha part, and you look at them as a pair. Okay? So you look at the collection of all pairs of the form n comma n alpha plus a, where n and a are integers. And let's just, yeah, that's fine. Okay? Now, if I'm thinking about these points as points inside of R2, then what can I say about this collection of points in R2? How is it sitting inside of R2? Well, it might help you to, did you guys have the answer? It might help you to think about it this way. If I take the set of all points of the form n comma n alpha plus a, where n and a are integers, that would be exactly the same as if I took z2 and multiply on the left, or multiply the, I don't know how to say this, if I take all the points in z2 and multiply from the left by the matrix 1 alpha 0 1. Okay?
Like a skew lattice?
It's a lattice in R2. Okay? I guess this is a big hint. This is the hint right here. It's a lattice in R2. And so just sort of recognizing this is one thing. This is not the kind of, this is just kind of like a Friday afternoon observation that you might make. And then the question is whether or not this is actually a useful observation. So let me say this is an, yeah, I'll just go ahead and say this is a 2 by 2 matrix with real coefficients. That's fine. Okay? Oh, well, that's not a 2 by 2. This is a lattice. Okay? I'll just erase that. So let's try to test this observation and see if it might be useful for proving some of the types of things that we want to look at. Let me give this matrix a name. Let me call it M sub alpha, 1 alpha 0 1. So this is a matrix, a 2 by 2 matrix with real coefficients. Okay, and for one, let's suppose that I want to prove a Dirichlet type theorem. Dirichlet type theorem. I'm not going to try to go for the full strength of Dirichlet's theorem the way that I first stated on the board, but let's suppose I want to prove something like this. For every alpha in R and for every natural number n, there exists a fraction a over n such that the distance from alpha to a over n is less than or equal to 1 over n times big N. I guess I should have said and the absolute value of n, or and the absolute value of n is less than or equal to n. Okay? Okay? So how can I formulate this statement in terms of my lattice? Well, if I just go ahead and multiply this inequality, multiply both sides of this inequality by n, what I get on the left-hand side is exactly absolute value of n alpha minus a. And so what does the statement of this theorem mean in terms of this lattice? Let me just try to draw you a picture for people who are trying to think about this. So here's R2. And here's my lattice. In one direction, it goes, I guess I'll just draw it this way. Okay. My points. So what does the theorem mean in terms of this lattice? It's actually supposed to be a lattice. I got off somewhere, but it's close. It's sort of close. It's close enough for you to get the picture. Well, here's the collection of blue points here is exactly the collection of points z2 times n alpha. Okay. And what the theorem is saying is, if I just reformulate it in terms of my lattice, it's saying that no matter what alpha I've chosen, and no matter what integer capital N I choose, there's always going to be a lattice point in the rectangular box that I've drawn here. This rectangular box is the box minus n cross minus 1 over n, 1 over n. Okay? Do you see what I'm trying to say? So what I'm trying to say is that the statement of this theorem here is equivalent to the statement that no matter what alpha I've chosen, and no matter what n I choose, there's always a non-zero lattice point inside of this box. Well, why is that necessarily true? Do you have a geometric reason why? Okay, well, there's a theorem. It's called the Minkowski convex body theorem. Some of you may have heard of it before. Who in here has heard of the Minkowski convex body theorem before? A few people? Yes? Okay. So this is called the Minkowski convex body theorem. I'll just go ahead and state it in generality here. Convex body theorem. What it says is that if lambda is a lattice in RD of covolume delta, okay, and if omega in RD is a convex, symmetric set. Symmetric means that if x is in omega, then minus x is in omega. Then omega contains a non-zero lattice point. Oh, I didn't finish the sentence there. It's a convex symmetric set of volume, at least 2 to the d times delta. Then omega contains a non-zero lattice point of lambda. Okay, you understand the statement of the theorem? So you should see why this theorem implies the theorem that I've written up here, the theorem that I've written right here. Okay, because the volume of the box is 4. I'm working in 2 dimensions. The box is rectangle that I've drawn here is a convex symmetric subset of R2, and the covolume of the lattice. The covolume of the lattice is the volume of a fundamental domain. So in this case, it's the determinant of the matrix that defines the lattice. So in this case, the covolume is 1. Since the rectangle that I've drawn has volume 4, I know that it contains a non-zero lattice point. And so non-zero lattice point in there means that I have a point which satisfies my inequality, no matter what big N and no matter what alpha I chose. Okay? So that's a very easy little cute observation. But with that in mind, we might want to sort of think about whether or not we can go a little bit further. how far can we push this idea of using lattices to study approximation properties of numbers? And we might want to ask ourselves whether or not we could use this idea to say something about the set of badly approximable numbers. Okay? I've tried explaining this before to some of you. So how do I characterize the collection of badly approximable numbers in terms of this lattice that I've drawn here? So alpha is a badly approximable number. Should I even say alpha is in bad epsilon? Alpha is in bad epsilon if and only if for every lattice point in my lattice, for every lattice point, lambda 1, lambda 2, in my lattice, minus 0. The product of the coordinates of the lattice point, lambda 1 times lambda 2, in absolute value, is no smaller than epsilon. Okay? So what does it mean in terms of this picture? What does it mean for alpha to be badly approximable? Where's that color that you guys said not to use? The red one? It's gone now? There it is. Okay. It means that you can choose an epsilon so that when you draw this hyperbola, xy equals epsilon, okay, and then reflect it around the axes, all of the non-zero lattice points that you see fall outside of that hyperbola. Okay. Okay. Well, this is still kind of in the realm of cool little observations, but this is something which can be turned into, which can be connected in a pretty powerful way to dynamics on the space of lattices in R2. And I want to try to explain that really quickly here. By the way, does anybody know what time I started? It's about 20 after, right? So I have a few extra minutes. Okay, good. Okay. So here's the basic idea now. And I want you to try to understand this part, because this is going to link in directly to what Anthony is going to talk about in the exercise section, but also to basically all of Anish's lectures as well. And the idea here, I'm gonna say it in sort of two parts. Number one is you have to switch from thinking about the number alpha that you want to approximate to thinking about the lattice generated by the rows of that matrix M alpha. So how can I'm going to go ahead and write something on the board here, which is going to look a little bit mystical, and then I'm going to explain what it is. To thinking about the lattice lambda sub alpha equal SL2Z times M alpha. What is this object? Well, you know the rows of M alpha, they span a lot. The integer span of the rows is a lattice. We already said that. And the lattice, of course, is only unique up to a choice of basis. Left multiplication by any 2 by 2 integer matrix with determinant 1 is going to give you a new matrix whose rows span the same lattice. And so you can think about your lattice as being the coset SL2Z times M alpha in the space SL2R mod SL2Z. Okay? And I quotient on the left. Anthony, do you quotient on the left?
I quotiented on the right. Yeah.
No, it's okay. I'm going to still quotient on the left, and I have my reasons. I'll explain later what my reasons are. Okay, so I quotient on the left. So that's the reason why my coset has SL2Z right here on the left. Okay? Do you understand what I'm saying here in the first step? This is actually sort of important change of psychology. I'm thinking about a lattice in R2. And here this quantity x2, this is supposed to represent the space of lattices of determinant 1 in R2. Each one is determined by a 2 by 2 matrix with determinant 1 with real coefficients. And that matrix determines, that matrix is unique up to left multiplication by an element of SL2Z, which is why I can talk about the quotient space. Okay? More on that later. So once you've switched from thinking about your real number to thinking about this element of the space of unimodular lattices in R2, the second thing that you want to do is you want to consider a natural way of perturbing, smoothly perturbing, and this is the dynamics, the natural way of smoothly perturbing your lattice while preserving the property that you're interested in studying. Okay? Now let me try and say a few words about this. Okay, so to say a few words about this, in my next lecture I'm going to talk about lattices and locally compact groups. And I haven't really told you anything about the topology of the space. I just said it's a group, right? But it's actually a submanifold of R4. It has a natural topology. It's actually a locally compact group, so it has something called Haar measure. There's a natural measure which sits on the space. When you work in the quotient space, you pick a fundamental domain, and then you can have Haar measure on the quotient. And now, there's also a natural group action on this quotient space. And the natural group action is right multiplication by an element of SL2R. It's right multiplication by SL2R. So I have a locally compact group modulo a lattice. I'm quotienting on the left. There's a natural right group action, which is multiplication on the right by an element of SL2R. The quantity that I'm interested in preserving is the product of the entries, is the collection of all products of entries of the lattices that I see. And so number 2 here, consider a natural way of smoothly perturbing your lattice while preserving the property that you're interested in studying. Another way to sort of formulate this in this bigger picture is you want to think about what's the stabilizer of the right action that I described. What's the stabilizer of that form in terms of the right action that I just described? Okay, I don't know if you follow what I just now say, but this point number 2, it also comes up in lots of different problems in this subject, and it's also going to come up, I'm pretty sure, when Anish talks about the Oppenheim conjecture. You have some quadratic form, and you're interested in studying the collection of values. So what you say is instead of, first of all, I change my psychology so that now I'm thinking about something in the space of lattice, in a space of lattices. And then instead of studying this one object, I thicken up the set by considering the right action by some group which preserves the property that I'm interested in studying. Okay? Now let me fill in the details for this particular problem so that you can see how it works out in this case and what's the connection to this important theorem called Molle's compactness criterion. We've got 5 minutes. I think I can do it in 5 minutes plus epsilon. And hopefully epsilon will be tending to 0 and not infinity. So we'll try. That's probably enough space. So let me explain now how to do number 2 if you're interested in studying badly approximable numbers. The way of perturbing these lattices is, well, by using the geodesic flow on the space SL2R mod SL2Z, okay? By using right multiplication by diagonal matrices. So here it is. For t bigger than or equal to 0, let's let GT be the matrix e to the t, 0, 0, e to the minus t. This is a matrix in SL2R. It's got determinant 1. It's pretty easy to see, right? And now, think about what happens when you multiply your lattice lambda alpha on the right by this matrix GT. What do you get? Well, let me just do the multiplication. SL2Z times M alpha times GT. Well, I get exactly the lattice SL2Z times, what will it be? E to the t, yeah, that's right. And then e to the minus t alpha, and then e to the minus t, 0. Okay? So what does a generic point inside of this lattice look like? So a generic point inside of this lattice, looks like e to the t times n, e to the minus t times n alpha plus a, where n and a are integers. And the point here is that if I take a point in this lattice and I multiply together the two coordinates, I guess I don't, yeah, that's fine. This is the collection of all points in the lattice. So you can see what a generic point looks like. If I take a non-zero lattice point in this lattice and I multiply together the two coordinates, I get the e to the t and the e to the minus t cancel. So if I'm interested in studying the collection of all products of non-zero coordinates, of non-zero points in my lattice, studying this lattice is going to give me the same results as studying my original lattice. Okay? So now it follows from what we've said that alpha is badly approximable if and only if there exists an epsilon bigger than 0 such that for every lattice lambda in the set SL2Z M alpha GT, t bigger than or equal to 0, and for every lambda in lambda, which is not, every lambda in lambda which is not 0, okay? The product of the coordinates of lambda is bigger than or equal to epsilon. This is exactly what I just now told you, but I'm just writing it down in words, okay? This is just saying that right multiplication by GT preserves the collection of all products of coordinates of non-zero lattice points. And just to write it one more way, this is equivalent to the statement that there exists an epsilon bigger than 0 such that for every lambda in SL2Z M alpha times GT, t bigger than or equal to 0, the collection of lattice points Z2 lambda minus 0, I'll take out the 0 point, intersected with the ball of radius epsilon centered at 0 is the empty set. Okay? Do you understand this? There's a lot of quantifiers, but basically what it's saying, these are all different ways of saying the same thing. The last statement here says that let me tell you what the last statement says just in words one more time. To be in bad epsilon is equivalent to the statement that when you take your lattice and you consider the right action by GT, t bigger than or equal to 0, you get some orbit inside your space. No matter what, every point in the orbit is a lattice, represents a lattice in R2. No matter what lattice in R2 you're looking at, all of the non-zero lattice points that you see in that lattice fall outside of the hyperbola that I drew. Okay? So why is this a good thing to know? This is a good thing to know because this is a very nice and well understood dynamical system. So when I say z squared lambda, I mean the collection, because lambda is the collection of all lattice points. So I actually do want z squared lambda here. Yeah. So z squared. So I have to write down a matrix that represents lambda then. So I mean, if my matrix, I'll write here A B C D SL2Z. If lambda is this lattice, then Z2 lambda, when I write Z2 lambda, I really mean Z2 times the matrix A, B, C, D. And of course, the point is that it doesn't matter what representative you choose for the coset, because you have an SL2Z on the left-hand side. Okay? Is that clear? You're right, it's not completely obvious what I meant by that. Okay? Okay, I need to finish up. So to finish up, I'm going to tell you something called, I'm going to tell you an important theorem in dynamics, which is called Mahler's compactness criterion. And Anthony is going to elaborate on this a little bit. And there's also a more general form of this theorem, which I could tell you, but for now I'm just going to tell you the simple form that we need for this application. So this is from the 1940s. And what it says is that if you have a closed subset, a closed subset omega of x2 is compact if and only if there exists an epsilon bigger than 0 such that for every lambda in omega, for every lattice inside of omega, if I take z2 lambda minus the 0 vector, I will not see any other lattice points inside a ball of radius epsilon. Okay? Okay? So in words, what this means is that if the space SL2R mod SL2Z is some non-compact space, okay? Maybe if you want, I can draw it like this. It goes up forever, okay? And what Mahler's compactness criterion gives you is it gives you a way of characterizing when a closed subset of the space is actually bounded. It says if you have a closed subset of the space, it's going to be bounded if and only if the collection of all shortest non-zero vectors that you see for any lattice in the set that you're looking at is uniformly bounded away from 0. Okay? So in the problem that we have, we're starting with some lattice lambda alpha, and we're flowing out around this space, right? And sometimes we're going up into the non-compact part of the space, and sometimes we're coming back. I'll just draw, just to get this done with, I'll just draw it like this. And the characterization of being badly approximable is that our point is badly approximable if and only if the orbit under this GT action is bounded. All right? So it gives us a direct characterization in terms of this geodesic action on the upper half plane. Okay, I think I am very close to having to stop here. So let me tell you one more thing. Actually, let me go ahead and stop there, and I'll tell you the other thing that I was going to tell you next time. So I think I will go ahead and stop there, and I'll leave the rest of the exercise with Anthony. Okay, so that's all I'm going to tell you today, guys. Thank you.